Think about walking through your home in the middle of the night. Even in total darkness, your hand reaches out for a doorknob or steps around the corner of a table before you ever touch them. We take it for granted, but it raises a difficult question. How does the brain link the memory of where that furniture is to the actual space you're standing in right now? For decades, this ability to find our way without getting lost was considered one of the most significant unsolved mysteries in the study of the brain. It suggests that our experience of reality isn't just something we observe, it is something our minds are actively building from the inside out. In 1971, John O'Keefe began tracking individual neurons in the brains of rats as they moved through physical enclosures. Deep within the hippocampus, he found a group of neurons that only fired when the animal was in one highly specific location. He called these place cells. As the animal explored, different neurons triggered for different zones. This was the first physical evidence of a cognitive map, an internal geography of the world stored directly in the brain. O'Keefe eventually won a Nobel Prize for discovering what appeared to be the brain's core positioning system. It proved that the brain isn't just reacting to what the eyes see, it is maintaining a database of points in space, marking locations like pins on a map. However, these place cells have a limit. They identify specific points, but they don't provide a way for the brain to measure the actual distance between them. In 2005, May Britt and Edvard Moser looked deeper into a nearby region called the entorhinal cortex. They found a different kind of neuron. Unlike place cells, these grid cells fire in a perfectly regular hexagonal pattern that repeats across any environment. This hexagonal grid does not exist in the physical world. It is a mathematical structure generated entirely by the brain itself. This grid provides the brain with a metric for space. It allows animals to track distance and direction even without seeing external landmarks. By projecting this invisible coordinate system over reality, the brain makes the physical world something that can be calculated and navigated. By 2018, AI could beat humans at complex games, but still struggled with basic spatial navigation. To solve this, DeepMind researchers challenged a neural network to track its own position using only signals for speed and direction without giving it a map. They utilized a technique called dropout regularization to randomly silence parts of the network, which effectively simulated the noise found in biological systems. The results were startling. Under these conditions, the network spontaneously organized itself, growing digital grid units that behaved like the grid cells found in nature. The AI wasn't programmed to create a grid. Instead, the mathematics of navigation forced the network to evolve the same solution as the mammalian brain. Researchers then tested this grid-equipped agent in complex virtual reality mazes it had never seen before. By comparing its current grid code to a saved goal code, the agent was able to mathematically extract the exact distance and direction to its destination. This is called vector-based navigation. It allows for an as-the-crow-flies trajectory, meaning the agent is no longer limited to following the paths it has already walked. The AI began taking zero-shot shortcuts. It bypassed the established routes to take more direct, unvisited paths, outperforming even expert human players. These emergent grid cells provide a built-in metric for space, enabling the AI to plan routes and solve spatial problems like a living creature. This system isn't just for moving through physical rooms. Evidence suggests these maps are the foundation for how we think. The hippocampus and entorhinal cortex appear to use these same place and grid cells to map out time, memories, and even abstract concepts. When you plan a business strategy or recall a childhood event, you are essentially navigating an internal coordinate system of information. Human intelligence functions as a spatial engine, constantly moving through a multidimensional map of our own experiences. Today, AI navigation is mostly used for specific tools like self-driving cars or drones. Creating machines with these spontaneous grid architectures is about something larger. It's the first step toward giving AI world models that reason and imagine. It brings together the biological discoveries of the 1970s with the computing power of today, showing that both systems rely on the same mathematical principles to understand reality. Did the brain evolve a GPS system for navigation, or did navigation become the foundation of intelligence itself?